Hey, let's look at just one more colligative property calculation for a strong electrolyte. And instead of osmotic pressure, let's look at freezing point and freezing point depression. So let's go ahead and take a solution that is quarter molal, so that is to say 1/4 mole per kilogram of solvent of calcium chloride in water. So it's going to be an aqueous solution here. And we want to know what the freezing point is going to be. We're assuming our water is at 1 atmosphere pressure, so it normally freezes at 0. So we have to pull into our equation, right? So we know the freezing point depression is equal to Kf times by the molality, and now, right, we recognize the fact that if it's an ionic compound, then it can actually break apart into multiple things. So we got that Van Hoff factor here. Calcium chloride should break down into 3 things. So we've got calcium and chloride and a second chloride. So the Van Hoff factor should be 3 for this one, and our molar concentration was 0.25. And our freezing point constant for water, we've got to look up, but it's like 1.86 degrees C per molal. So if we take care of units, so molal cancel out, we're left with degrees C. That's pretty good for a temperature. And I calculate something like 1.395 degrees C. So in terms of significant figures, I probably should only have 2. You might say, well, why not 1, right? Because doesn't that have 1? Well, that's an exact counted number, I suppose. So theoretically, it should break into 3, and it's exactly 3, right? A calcium, a chloride, and another chloride. So what is the freezing point? It's not 1.395 degrees C. Remember, that is the depression. So the actual freezing point, right, is the ideal freezing point minus this depression. And it actually freezes at 0 exactly, so 0.0000 degrees C, right? And we are lowering it by 1.395 degrees C. And again, I think at the end of the day, right, if we keep track of significant figures and everything, it should be minus 1.4 degrees C. Awesome. So if you actually do an experiment and you measure the freezing point, maybe you get a freezing point that is minus, say, 1.3 degrees C. And is that something that's likely to happen? Well, we know that sometimes our theory and our experiments are a little bit different, but it turns out that oftentimes it won't be as big as we predict. And the reason for that is actually we've assumed a theoretical Van Hoff factor of 3. So let's calculate the Van Hoff factor for this situation, and let's try and figure out what's actually going on. So we can start with our original equation. So delta T is equal to I times Kf times by M. Okay, sorry, I've moved the terms around here. So I is equal to delta T over Kf M. We need a little bit more room here. All right, sorry, I just had to push the canvas up there. So I can calculate my Van Hoff factor. So I'm actually getting a freezing point depression of 1.3. Remember, it's gone down by that. So it started at 0. It went down to minus 1.3. So that's a 1.3 depression. Kf we saw earlier was 1.86 degrees C per molal. And the molal concentration we started with was 0.25 molal. So if we look at our units here, there is nothing surviving. And the Van Hoff factor is just simply the number of particles it's breaking down into. So let's go ahead and calculate that. So my calculator says that is something like 2.8. And so that's less than 3, right? So how can it be breaking down into 2.8 particles? And the answer is, and it was not much of an answer really, if I just write a word down, is there's something going on called ion pairing. And that is to say that the ions don't completely break down. In fact, what you find is that occasionally the calcium ions and the chloride ions will kind of stick together in solution, and when they stick together they'll form a pair. So instead of having maybe 3 separate ions, every now and again in solution one of the chloride and one of the calciums will kind of stick together, and they will kind of move around like a little charged molecule. So instead of 3 different things, you'll have 2 different things. And of course, why isn't that then 2? Well, not all of the calciums will pair up with the chlorides. So let me show you a figure on the next page, and then we'll call it a day. Okay, so this is a figure of what sodium chloride might look like in solution. So sodium chloride, right, presumably breaks down to 2 ions. And there's my sodium ion and there's my chloride ion. So the Van Hoff factor would be 2. But what we see is on occasion, right, these ions are a little bit too close to each other, and they kind of get stuck in each other's orbits, and they behave like one individual unit. So on average, right, you'll have a little bit less than the theoretical number of ions in solution. As these solutions get more and more concentrated, there's just a bigger and bigger chance they'll end up next to each other other, and this ion pairing will happen. So let's go ahead and throw that to one side and look at this table here. So this is a 0.05 mol solution of a non-electrolyte, which doesn't break down. And if you look at sodium chloride, we would expect it to break down into two pieces, but in actual fact, when we measure the Van 't Hoff factor, it's 1.9. So it's a little bit less because of these ion pairs being formed. And as we go to something like magnesium sulfate, we'd expect it to break down into magnesium and sulfate. That's two ions, but in reality, it only breaks down on average to 1.3. And why is that? Well, the magnesium's charge is 2 positive, sulfate's 2 minus, so they stick together a little more frequently in solution. And so on average, there's only 1.3 ions for every formula unit being made. Magnesium chloride, again, you might expect it to break into three things: magnesium, chloride, and chloride. So the theoretical value is 3, but in reality, it's a little bit less. And again, that highly charged magnesium, right? The bigger the charge, the more the attractions, the more those intermolecular forces, kind of forces them to occasionally stay together. And so you're only getting 2.7 on average. So there's potassium sulfate. Again, we'd expect 3. We see 2.6. Iron 3 chloride, again, that big 3 positive ion there will pull some chlorides into its orbit on occasion. And so instead of having on average 4, you have only, say, 3.4. And the actual numbers themselves, you certainly don't have to memorize those. You don't have to know them anything. I will never say, what's the Van 't Hoff factor for 0.05 mol sodium chloride. There's no way I would expect anyone to know. I have no idea what those numbers are myself. But the general idea is that they'll always be smaller than the theoretical because of these ion pairings, this effect that the ions can occasionally find themselves stuck next to each other in solution.